Professor Ortiz, the floor is yours.
Thank you. Thank you very much. Can you hear me? Is this working? Okay, good. Big data, data science. Okay, so something that we hear every day. It seems to be an emerging phenomenon. Probably every transaction we ever make on the internet and with your cell phone is recorded somewhere. So in a way, big data has replaced Big Brother, and companies are sitting on mountains of data that they use for many purposes. So, and the techniques that have been developed in connection with this data-rich environment, this new data-rich environment, have come to be known as data science. And so generally, data science is the extraction of knowledge, let's say something useful from large quantities of data. It's based on mathematical algorithms, basically traditional statistics, okay, by different names, to extract insights from the data. And it's used mainly in non-STEM fields associated with marketing, okay, so of course these fields use the data that I referred to at the beginning to reach you and target ads, personalize them to you. And so it's been an established field already in non-STEM areas for quite some time, okay? Areas like marketing, advertising, finance, social sciences, also, of course, security and cybersecurity, security, medical informatics, and so on. These basically applications of traditional statistics. Okay, there is no science in it. And the question is, as scientists and engineers, is there anything in it for us? Okay, should we be prepared for the onslaught of big science? Okay, and so in a way, this started thinking about this some years ago, and I started talking about this subject here in Complas 2 years ago, and what I'm going to show today is what we have done in the meantime. Okay, and so what is different about what we do is that, as I was saying, we are scientists, and we work in science and engineering, and the problems that we deal with have a very, very definite mathematical structure. They're not just problems of statistical inference, okay, but there are some equations that are completely universal, material-free, and they're non-negotiable, okay, so those are, for instance, in the case of elasticity, which is going to be the running example throughout the presentation, but in many other fields as well have exactly the same structure. You would have things like kinematics, okay, so that's essentially geometry. So again, there is nothing that is material dependent about that. It's completely material free and universal. And then you have equilibrium, that's sum of forces equals zero. Okay, no matter what, okay, that's always non-negotiable, okay, I don't care what the material is, but forces have to add to zero. So this provides a very definite and very specific mathematical framework for everything that we do, okay, so these are universal relations, universal meaning here material independent. And then, of course, okay, these equations are not closed, okay, they're deficient, rank deficient if you want, so we have to close them with a material law. And here's where really the drama lies, okay, and the epistemic uncertainty problems all arise in our field, mainly in connection with imperfect knowledge of the material law. Of course, there can be also uncertainty, parametric uncertainty regarding the loads, regarding the geometry, okay, and in some applications that may be important, but that's not what I'm talking about here. I'm talking about situations where all the uncertainty, really epistemic uncertainty, so lack of knowledge really comes from the material law. Okay, so I mean this here you recognize the equations of linear elasticity, okay, if you want, but the same structure, of course, is found in many other areas of science and technology, okay, so I would say all field equations of science basically have this structure. Okay, you have some conservation laws and some localization laws that are conjugate to each other, that are adjoint to each other. And then you close those equations by some kind of material law. Okay, epistemic uncertainty, here's where all the sausage making takes place. Okay, so modeling, fitting, and so on. And so we need to generate something there. We need to close the equation. So we have to provide a material law, okay? Otherwise, the boundary value problem is not well defined. And the traditional paradigm was to gather data from various sources, okay, and make educated guesses about the material behavior. We call those material laws. Those material laws depend on parameters. Empirical interatomic potentials would be another example, really. I mean, this is not specific to continuum mechanics. And then you fit. You fit to the data. You can call these training sets. You can call them anything you want. You can call the fitting anything you want. You can call it regression. You can call it machine learning. You can call it model reduction, central manifolds. Still fitting. Fitting by any other name is still fitting, okay? You're taking data and you're replacing it by something else, okay? So, and then we use the calibrated empirical models in boundary value problems. That's been the traditional paradigm, and there is nothing wrong with it. Fitting may be a fitting thing to do in some cases, so I'm not saying that fitting is bad. We're just trying to explore alternative paradigms, okay, in this data-rich environment that we have today. Okay, and so this is another way of understanding the flow of data in terms of material behavior. So in the traditional paradigm, so traditionally the data was scarce, so typically we would have 2 points, and all we could do is to draw a straight line through the points. That was the extent of fitting. Now, because of advances in diagnostics, so we have three-dimensional full field diagnostics of many kinds, and also because of data mining in terms of multi-scale modeling, so we can use fundamental theory, okay, like DFT and so on, to generate data. We're really sitting on a mountain of data here. Okay, so we have lots and lots of material data, or something you can call data. Okay, and what we do at the end of the day when we generate and calibrate a model is to throw away all this data and replace it by maybe one or two constants, a couple of Lamé constants. So there's a huge loss of information in going from the material data that you have in your material database to the material model. Then you put that into your solver. It could be, for instance, a finite element model, and then you generate a lot of data, manufactured data. So you have a kind of a double funnel kind of approach instead of the inverted funnel of the traditional, the old days. Okay, now you have a double funnel where you have a lot of material data, you throw it away, and then you generate manufactured data. And there is essentially a broken pipe. Okay, so if you think about it, when we do scientific computing, we're really mapping material data into outcomes. Okay, so there is somehow some mapping between the data and the manufactured data, or the outcomes about the system. And in the traditional paradigm, this pipe is broken. Okay, so we would like to find something else, something that replaces this paradigm where you have, it's kind of a lossless approach where you really lose no information in going from material data to manufactured data. Okay, so we live in a data-rich world. Okay, that's really a sea change. I mean, it's completely different from when I was starting out in the field, for instance, as I said, and it's something we have to adapt to one way or another. And what we're seeking is a data-driven paradigm, so a way of doing computing where you use the material data, the raw material data, unprocessed, directly with no loss of data in your calculations, okay? So no fitting of any name or by any name, okay? Fitting by any name, any other name, still fitting. No loss of information, no broken pipe between material data and manufactured data. That's what we're looking for. Okay, so the question is how? These are nice words, okay? Talk is cheap. So what I like to say is math talks, nonsense walks. So can you put these nice words in a mathematical framework? Okay, otherwise you have nothing. So, okay, so this, again, the solution is not unique. And what I'm going to present is one possible way of mathematizing the problem, okay? In a way that at the end of the day you can do calculations in a reliable way. Okay, so I'll start with a parable, okay, with a simple example. So just describing the method with a very, very simple case, which is a one-dimensional case where you have a bar, okay, we're engineers, we like bars, okay, of all types. And so say that we load the bar with a loading device, okay, that has some stiffness, okay, just to make things general. And so here the solution that we seek is not a displacement solution, so this is not a displacement method, but really we're looking for the state of the material. So the state of the material is going to reside in some phase space of work conjugate variables. In this case, because we're doing elasticity, it would be a strain and a stress. Okay, so we call this phase space, and that's where we seek solutions. So here you already see a departure from the traditional energy minimizing, say, minimum potential energy approach, where the primary unknown is the displacement field. Now, so we have equilibrium, we have compatibility. Again, those are non-negotiable. If you work those out with this loading device, you have this relation, simple relation between the stress in the bar and the strain in the bar. This is just the stiffness of the loading device and so on. Okay? So this defines a constraint set in phase space sigma epsilon where the solution has to reside. And again, that's a hard constraint. So that's a constraint set, and then we have a material data set. Say that we have a classical model where the classical model is a graph in phase space, so that means a curve. So we know that all admissible states of the material have to be on this graph. Okay, then of course the classical solution is just the intersection, and we're done. Okay? Fine, so that's the ancient regime, okay? So now let's say that you don't have a model, but all you have is data. So the net sum knowledge that you know about your material resides in a point set of data. And this is all you have. Of course, traditionally you would fit a graph through and you would go back to the previous case. Let's say you don't want to do that. You want to use these points directly in identifying a reasonable solution. Okay, so in general, okay, so you won't have any classical solutions in the sense of that generally there won't be any point in the data set that is both in equilibrium and is compatible. So the intersection, so the classical paradigm fails and there is no solution. In situations where you might expect reasonably a solution to exist, somehow, okay, you expect the bar to be somewhere in there, okay, just by the naked eye. Okay, so what we do instead of this overly rigid definition of solution is to say, okay, so we accept a solution, the point in the data set that is closest. This should be the constraint set. Okay, so D is the data set and E is the constraint set. So we accept as the solution the point of the constraint set. So a strain and a stress that are compatible and in equilibrium that is closest to the material data set. So that kind of softens the definition of solution, and then as you can see, of course, in this case, you will have a solution, which will be the point in the data set that is closest to the constraint manifold. Okay, so we have regularized the concept of solution, and now we can make sense of problems like this, where you have, again, hard differential constraints, okay, and just a data set. And note that we have defined a solution here without any fitting. So we haven't done any modeling. We haven't put any lines through, okay? So we have completely bypassed the modeling stage, which, you know, inevitably always adds uncertainty into the picture. We use the raw data directly, okay? So this is the one possible definition of data-driven computing, distance-based. And so you have a material data set, you have a constraint set, which is all the local states that are compatible and in equilibrium, and you seek the point in the constraint set, so the point in phase space that is compatible and in equilibrium that is closest to the data set. And that's what I just said. Okay, so again, I'm hammering the point. No material modeling, no data fitting, no VNV. Okay, thank goodness. VNV was never clear. So I never knew what VNV exactly meant. So you throw VNV out the window, good riddance. Okay? And you use the raw material data directly, unprocessed, in calculations. The facts, nothing but the facts. So that, you know, paraphrasing an old TV show, the facts, nothing but the facts. Okay, so the first question then, so there are any number of questions of course, that arise. Okay, some questions in analysis, some questions in computational science, if you want. Okay, so let me just say a couple of words about analysis. So first of all, we have redefined, really, if you think about this, is really a redefinition of the classical problems of science and engineering. Okay, so it's a complete redefinition of those problems. Are the new problems, okay, these data-driven problems, well posed? I mean, that's the first order of business, because if they happen to be ill posed, why bother trying to solve them or trying to do approximations, or numerical approximations? So one of the things that we've looked at with my new bodies in the Hausdorff Institute for Mathematics in Universität Bonn is the problem of well-posedness. So here, if you look at the problem of linear elasticity, okay, data-driven elasticity from a mathematical point of view, you're looking for solutions in a space of linear functions, in this case, which is strains in L2 and stresses in L2. I mean, that's really your global phase space where you want solutions. And then the constraint set, what I called previously E, are all the strain fields and stress fields that are compatible, in particular with the boundary data on the Dirichlet part of the boundary, and in equilibrium, in equilibrium with body forces and applied tractions. And okay, so let's say that we have a classical material law, which means a graph in phase space, and the graph could be just linear, for instance, linear Hooke's law. It could be any monotone function. Okay? So now we have the problem of finding the point in this linear space that is closest to this data set, okay, defined here. Okay, so this is the data-driven problem now in this kind of functional analytical framework, okay, and then you make some reasonable functions about the regularity of the domain, regularity of the forcing. I mean, these are just conventional assumptions of linear elasticity. And what you find is that, in fact, the data-driven elasticity problem indeed has a solution. The solution is unique and, in fact, coincides with the classical solution. So this redefinition of continuum mechanics is well posed. Okay? It's not crazy, in other words. So it's worth looking into in terms of finding analytical solutions and in terms of approximation. Of course, you would expect also some continuity with respect to the data set. So if you have, say, a sequence of data sets in the form of a sequence of points that somehow converge to the red line, you might expect the data-driven solutions from this sequence of material data sets to somehow converge to the solution of the limiting model. And in fact, that's the case. So one very nice thing from the standpoint of analysis, the data-driven analysis really introduces is a notion of convergence with respect to data sets. So if you have data sets that converge uniformly in this sense, that all the points lie in a sausage of the limiting model, okay, which becomes thinner and thinner, and the sausage is uniformly sampled by the points, then you find that the data-driven solutions, in fact, converge to the classical solution in the limit. Okay, so there is a very, very nice sense of convergence with respect to the data set. Okay, so the data-driven problems, then you can say, represent a complete reformulation of the classical problems of mechanics. Okay, so a different way of doing things. Also from the analytical point of view. It's not just a computational hack. It's really a different viewpoint, even from the standpoint of analysis. And it's a viewpoint that is really general. Okay, it contains special cases, all the classical problems, where you have many other problems where the data set is not necessarily a graph, but it could be a collection of points, could be a fat set, could be a graph that closes on itself. Okay, and so data-driven problems are more general than classical problems. Subsume the classical problems, and you recover the classical solutions whenever you have a classical problem. Okay, so it leads to a number of interesting concepts in analysis, convergence with respect to data, and relaxation. So what you see, okay, this is a completely different talk, but that the notion of micro-macro, I think, like the French call this, so relaxation Okay, it's completely different in data-driven. You get completely different effective models at the macroscopic level, okay, when you start with the same microscopic model that you would get from the classical picture. So it also introduces a different notion of relaxation, micro-macro, okay? Anyway, so there are interesting opportunities from the analysis point of view. And, of course, there is the computational side. So let me show you a couple of things that we've done from the computational point of view. So a simple example of application could be trusses. Okay, so this is finite dimensional, so we're no longer in spaces of functions, we're in a Rn. And the phase field of the truss is very simple because you have a uniaxial state of stress, so you have one uniaxial strain and you have one uniaxial stress. So you imagine every truss member, okay, to be characterized as a material by a collection of data points. Okay, and then you apply, for instance, the distance-driven or distance-based data-driven approach that I described earlier, and you're off to the races. And basically what that means is that, okay, you have nodal degrees of freedom, then your phase space in this case is going to be a collection of states of all the truss members. You introduce a distance in phase space, which is just an L2 distance. The constraint set in this case is given by the B matrix. Okay, so this conventional, structural mechanics. The equilibrium constraint is just B transpose sigma equals F. Compatibility constraint E equals B times U. Okay, so it's conventional structural mechanics, and then the problem is to minimize this distance between all these admissible sets that are compatible and in equilibrium, the distance of all those sets to the data, the material data set. Okay, this minimization is a double minimization. The inner one is just structural mechanics, or the usual variety. Here you can plug in all your standard structural solvers. And then in addition, you have a material data set where you're trying to find for every member, every truss member, the nearest point in the material data set. So we implement that as a double iteration, a staggered iteration, where, again, the inner iteration, once you have an association between truss members and material points, then you have a standard truss analysis problem that gives you the state of all the members. So this would be, for instance, the state of member E lying here, and then you redo the material data association by going, for instance, to the nearest point in the material data set, and then you do this iteration until you have convergence. Convergence means that you have a mechanical state that is compatible and in equilibrium, and where the material associations no longer change. Okay? So here's just it's just a simple example of how that iteration works. Yeah. It's a very simple, just two-element problem with, say, an applied force. Then, of course, by equilibrium, the stresses of the truss members have to be equal. So you see that these are the material states. They're on the constraint manifold, which in this case is a horizontal line. And the circles are just a distance function that are shooting out and searching for the nearest point in the data set, which are the blue points. And you can see the iteration working itself towards convergence, and the convergence finally is the point on the constraint manifold, the point on the data set that is nearest to the constraint manifold. Okay, so that would be a possible visualization. This is the same example for constraint displacements. Okay, and so now you have a simple example you can run, and you, of course, verify that this material point association iteration converges. Okay, so here we have data sets of different sizes. This is the truss example. This is the convergence of the iteration that I just described. And you can see that it converges linearly, as you would expect from a fixed point kind of iteration. Okay, but convergence nevertheless. There may be much better iterations to do this based on range query sets, for instance, in material phase space. I mean, there are many issues of high-performance computing that we haven't explored at all, okay? And this is just an illustration of convergence with respect to the data set. This is uniform convergence. You have sequences of points that are denser and denser and closer to a limiting graph, as you can see. So this is just an instance of the theorem, that it is the example that proves the theorem, if you want. Okay, and you can see that, of course, okay, under these conditions of uniform convergence, the error, okay, meaning the distance to the classical solution, goes down to 0 with a number of data points. Again, so it's the kind of convergence you might expect from the general theorem that I described earlier. So this all is expected. So these are what we call now distance-based DD solvers, exhibit good convergence with respect to material data associations, with respect to data convergence. Okay, so they're insensitive to data noise in particular, as long as that data noise is uniformly distributed. But they have a problem. Okay, so that has led us to explore generalizations of these distance-based DD solvers that I just described. The problem of the distance-based DD solvers is that they are overly sensitive to outliers. Okay, and if outliers cannot be ruled out, then distance-based DD solvers need to be generalized and extended. And what I mean by that, just with pictures, is that, okay, this is what I just described, okay, a situation where somehow the data is in a narrow sausage. So if this were part of a sequence of data, it would be uniform convergence towards a graph. Okay, and the distance-based DD solvers work perfect with respect to this kind of data convergence. But you could have an outlier, just one point. So, of course, in a democracy, a single point shouldn't matter. But distance-based solvers, unfortunately, are not democratic. They're really subject to the tyranny of the outliers. So, okay, so you have a situation like this, where this is the constraint set. Again, you would expect somehow the solution to be here, because you have many, many voters there voting for the solution, okay? That's what our eye would say, but okay, so long as you have an outlier that is just infinitesimally closer to the constraint set than any of these, say, normal points, then the outlier wins. Okay, and so maybe this, okay, maybe it's not. Okay, so we would like some other data-driven solvers that are insensitive with respect to outliers. And okay, so this is what we, okay, so we just said that data-based DD solvers suffer from the tyranny of outliers, and we can eliminate that tyranny basically by doing a cluster analysis, by looking not at individual points, but clusters of points. There is a standard way of doing that, which is called maxent inference, which is replacing the distance between points by this thermalized distance, okay, that assigns to every point a given weight. The weight that is assigned to each point in the material data set relative to a point on the constraint set is exponentially decreasing, okay, in this maxent inference approach, but all the points have a say. How much say the distance points have depend on this pseudo temperature, okay, or inverse temperature. The 1 over the square root of beta is kind of a radius of influence, okay, so you can make this model closer to a distance-based DD as you want by taking beta large, okay, but generally for a finite data, this provides a softer version of the DD. Okay, so now you, of course, you minimize the distance of the data set in the constraint set. And typically what we do is we start from a very high temperature, then things are easy, you know, things are very democratic, all the points in the data set have a say, and then we do simulated annealing. So we kind of converge towards the solution of the data-driven, but we, in the process, the distance-driven, in the process we kind of drive outliers out of business. And this is just more or less how this example, I mean, this works. So by that thermalized distance now, so the big clusters win, and you're going to get a solution here that lies basically in the thick of things. And the outliers, as I said, are driven out of business. Okay, so clusters dominate now. This is just an example to show how this works. Almost done. So what this is showing again is that very simple, for purposes of visualization, 2-bar problem with applied force. So therefore, the constraint set is a horizontal point. The 2 bars are different, so the levels of stress are different. And as you can see, by simulated annealing, we start from a very high temperature. So that means that lots and lots of points in the data set, which is a noisy data set, influence the solution. Okay, but as we reduce the temperature, then as you can see in the end, only a very small cluster of points influences the solution, and you get solutions that are both in the constraint set, that are compatible and in equilibrium, and they're basically centered with respect to the data set. Okay, so this would be typical application of the maxent solver. Does it work? Yes, it works. So okay, we can check convergence. Okay, with respect to data sets that become narrower and narrower. Okay, with respect to a limiting model. Okay, so then if you measure the model, the distance or the error between the noisy solution and the classical limit, then you find that in fact you have rather robust convergence. Okay, so linear convergence, which is what you would expect, or something like it. Okay. And so the method works, and again, removes the tyranny of the outliers. Okay, so that's another possibility as regards data-driven calculations. There are many extensions, for instance, to dynamics here. The extension to dynamics is basically trivial and for free. The only thing you have to do is you have to replace the equilibrium equation by the equation of motion, time-discretized equation of motion, so say Newmark. Okay, so you replace the equation of equilibrium in the definition of the constraint set by, say, Newmark. Okay, so that is another constraint set that works incrementally, and then you can, again, with a very noisy data set, you can see again how the data set is covered. You can get dynamical solutions, and the extension is quite trivial. You see a comparison here between the noisy solution and the solution of the backbone model, and you can see how close they are. I mean, they're incredibly close, closer than I would have expected, but it shows how you can actually do data-driven dynamics in a reliable way with rather noisy data sets. Okay, so I think that's all the time that I have, more or less, so let me leave you with some parting shots. So I think data-driven computing is emerging as an alternative paradigm, okay, to model-based computing. So now we have 2 paradigms. One is traditional one, which is based on fitting and using a model. That can be a fitting thing to do, as I said. And you have the new paradigm, which is use the data directly, forget about the modeling. Okay, there are pros and cons, okay, but it's nice to have options, I would say. We have shown that data-driven computing actually can reliably supply solutions from raw material data sets. You just take the material data set from first principles, from experimental, and you plug it directly in your calculations. No intermediate steps. And you can do that reliably and accurately. And I think that's a train that is basically unstoppable, okay, because I think data-driven computing is really likely to be a growth area because we are in an increasingly data-rich world. Okay, we really literally sit on mountains of data. Okay, and so I think it behooves us as a community to actually get ready and get on the program. Okay, so I mean, big data is there. We have to figure out what best to do with it. Okay. There are numerous outstanding questions. Okay, so for instance, the first one is the question of phase space coverage. Typically, okay, phase spaces are high dimensionality. You cannot cover them uniformly. You don't need to. Okay, this is a classical problem in physics. For instance, calculation of a partition function. It's an integral that you have to do in very high dimensional space. You don't cover the space uniformly. Okay, you do what is known as importance sampling. So here the analogous notion is the notion of goal-oriented material data sampling. So you want to sample the phase space in a way that covers your application, okay? Not uniformly because that's impossible, but in a goal-oriented way. I mean, again, that sounds like nice words, but I would like to mention here the NAND group. Where is the NAND group? They're here somewhere. They've really come up with something very, very clever where they tie data-driven analysis to experimental testing. And what they do is they measure both strains and displacements. Basically, they over-constrain the system. And that way, by running many relevant loading cases, they can populate in a very accurate way. I mean, it's really amazing how it works, a material data set that is tailored to that class of applications. So I would say that it's already been done, and it really works very well, and you can actually generate data sets that are goal-oriented and targeted to provide adequate coverage for a particular application. And then, of course, the 500-pound gorilla in the room is inelasticity, time dependence. There, if you want to adhere to a strict data-driven concept and you don't want to do any assumptions as regards material modeling, then basically what happens is that the response at any given point is a function of the entire history prior to that point, and the data set really should be a collection of histories. Now, how to do that? Again, math talks and nonsense walks. It's something that is work in progress, and maybe in 2 years, okay, in Complas 18, we'll be able to report something. So thank you very much.